This is content of part 2. If you're interested in only a specific part of this video, just jump to its start time. Next, I will talk about measurement of the strength of the Pma and strength of the spin-orbit interaction. I will only talk about nanomagnet with a perpendicular to plane equilibrium magnetization. However, the same measurement can be used for nanomagnet with the in-plane magnetization. In equilibrium, there is an intrinsic magnetic field which holds magnetization perpendicular to plane, also called along the magnetic z-axis. The measurement of the strength of Pma means a measure how strongly that magnetic field holds the magnetization along its z-axis. The measurement of the Pma strength is rather straightforward. An external magnetic field is applied perpendicular to the z-axis. The strength of external magnetic field, which is required to tilt the magnetization at fixed angle, measures the Pma strength. When the Pma is stronger and therefore intrinsic field is larger, a larger external field is required to tilt the magnetization. When the Pma is weaker and the intrinsic field is smaller, a smaller external field is required to tilt the magnetization at the same angle. Next, I will talk about the measurement of the spin-orbit interaction. The perpendicular magnetic anisotropy, the Pma, is induced by spin-orbit interaction. As I described before, the spin-orbit interaction is proportional to external magnetic field. When there is only one magnetic field, which is intrinsic magnetic field, the spin-orbit interaction is proportional only to this intrinsic field. In order to measure the strength of the spin-orbit interaction, an additional external magnetic field should be applied in parallel to the intrinsic magnetic field. In this case, the magnetic field of spin-orbit interaction, and therefore the Pma strength, is proportional to the total magnetic field, which is the sum of intrinsic and external magnetic fields. A measurement of the Pma strength versus external magnetic field gives a proportionality coefficient, which is in fact the coefficient of the spin-orbit interaction. It means that for this measurement, two types of external magnetic field are required. The first magnetic field should be directed in plane, and the second field should be perpendicular to plane. For each fixed perpendicular magnetic field, the in-plane magnetic field should be scanned, and the Pma strength should be found. The proportionality coefficient between Pma strength and the perpendicular external magnetic field gives the strength of spin-orbit interaction. In this measurement, it's necessary to measure inclination angle of magnetization when the external magnetic field is scanned. Magnetization inclination angle can be measured by several different methods, for example, from magnetoresistance of a magnetic tunnel junction. I did the most of my measurements using the Hall effect. In this case, a nanomagnet made of a magnetic metal like iron boron is fabricated on top of nanowire made of non-magnetic metal like tantalum. A DC voltage is applied to the nanowire and DC electrical current flows through the nanowire. The Hall voltage is measured by a voltmeter. The Hall voltage is linearly proportional to perpendicular components of the magnetization. The Hall voltage is largest when the magnetization is perpendicular to the plane, and there is no Hall voltage when the magnetization is in plane. The magnetization inclination angle is calculated from measured Hall voltage. Often I do two measurements when the magnetization inclined along and perpendicularly to the current direction, The evaluated strengths of the Pma and the spin-orbit interaction are the same for both measurements. However, the measured magnetic field, which is induced by accumulated spin-polarized electrons, are different for each measurement. I will talk more about it later. As I have mentioned before, during each measurement I applied a fixed magnetic field Hz perpendicular to the plane while scanning in plane magnetic field. Therefore, the strength of Pma and spin-orbit interaction are evaluated for several values of Hz. Next, I would like to mention a very important fact which substantially helps this measurement. Fact is that in plane component of magnetization is linearly proportional to applying plane external magnetic field. This is just sign of magnetizational angle with respect to film normal. This is in plane magnetic field, and it is proportionality coefficient, and the proportionality coefficient called the anisotropy field. It means that the magnetization is perpendicular in absence of external field, and it tilts towards the field, so the magnetization component along the field is linearly proportional to the field. When the external field is equal to anisotropy field, the magnetization is done fully in plane. These triangles show the experimental data. As you can see, the experimentally measured dependence is very linear. This substantially simplifies the analysis of measured data because the linear dependency is very easy to fit. As you will see later, there is also a nonlinear contribution to this linear dependence, and even an oscillating contribution which is induced by the interface. However, this contribution less than 1% from the linear contribution, and the linear contribution could be considered as a good first approximation. Next, I will explain the reason why we have such a specific linear dependency when the in-plane component of magnetization is linearly proportional to the in-plane component of the applied external magnetic field. The reason why is simple and straightforward. It is because of the linear dependency between the spin-orbit magnetic field and the total applied magnetic field, where the total magnetic field is the sum of the internal and external magnetic fields. The mass which proves the relation between spin-orbit interaction and the Pma can be found in my web page about the Pma. Just on the top of the page, below content, there is a PDF file. Just open it. All detailed mass is in there. The mass is rather simple and straightforward. The anisotropy field in the magnetization direction is calculated from the condition of minimizing the magnetic energy. There are 4 magnetic fields which contribute to the magnetic energy. Fields are external magnetic field induced by the magnetic moment, magnetic field of the spin-orbit interaction, and demagnetization field. I have tried to describe all the steps of the mass in as much detail as possible. You can follow the mass just by eyes without use of a pen. The key finding of this mass is that the spin orbit should be linearly proportional to the sum of other magnetic field in order for formulas to fit experimental data. If you are interested to see the content and other parts of this video, you can find the links below this video.